Right. Can you check if the stream's up?
Yeah. Yeah, it's up.
Perfect. That's not let me kind of go back to this thing.
Yeah, it's good. Just go whenever. It's all right, dude. Just keep it, I think.
All right, so this is our second lecture for today. We're gonna be doing PyTorch 2. Oh, if you look at the stream, it's like zoomed in. So today we're gonna go do into the second set of PyTorch fundamentals, kind of diving into attention and everything. Um, so kind of like a bit of an introduction. I'll kind of speed through this since we're already past time. I'm Kartik. I'm one of the ML lecturers. This is Alvin. He's the education lead. And so basically a recap of what we did last time. I don't know if we can raise the brightness or something here. It's a bit dim, but basically we covered tensors, which is a core data structure for a lot of ML stuff. We covered automatic gradients and computations. We covered and module class, which is standard model abstraction for how we can kind of define models. We can use object-oriented programming, kind of the superclass that's given to us by PyTorch. And then we cover the training loop for how to update these models using the backpropagation algorithm. And then so kind of learn how to build models. Today we're going to build understand what type of models are kind of used in industry right now, specifically some of these attention networks and transformers. Um, so this image is kind of a bit cut out, but this is basically a convolutional neural network that's used for a lot of image detection. And here we have what is kind of like a convolutional kernel, where instead of sequentially analyzing the image pixel by pixel and squashing it to, let's say in this case, it's around 7 by 7, instead of a 49 dimensional image, we kind of look at it from a shape of, okay, we take kernels, we slide it across, and we have some sort of computation formulation where we have, okay, the new pixel value is like based off of the nearby regions. So you're kind of looking at an image kind of like how a human would with regions. And so this is why this type of convolutional neural network is successful for images. Um, but again, this type of network isn't really useful for text. The main one that's useful for text is transformers intention. But the preceding network to this was recurrent neural nets, and these basically operate by where you take, okay, the previous state um, of your output or your network, and then you filter it into the next state. So you see this in a lot of time series forecasting, a lot of time-based data. But the issue with this is if you were to analyze some sort of text, right, and all the A's are words in a sentence, so we say, the cat had a house, right? If you're interpreting the value of the word house, you're basically relying sequentially upon the words the cat had, um, and so as a period of time, over a period of time, the value of these words or how it influences kind of lessens. So in a way where like, okay, when we're looking at a sequence of words, we're not interpreting it word by word, one at a time. Whereas the human brain tends to naturally just look at it all at once and kind of understand the value. And that's kind of where we get this idea of, okay, how do we develop attention-based networks where we can kind of look at everything simultaneously, have some sort of matrix operations, and get those values for each individual word at the same exact time. And we don't have a recency bias where, okay, the most recently calculated words are the ones that are kind of correlating to our projection right now. So why do we need something new for text again? The CNNs are very useful for images, but they're good for detecting local patterns, regions, kind of like the kernels that we talked about. And then the RNNs are slow and sequential processing. We forget long range info over a period of time. And again, if you have like a piece of like a sentence or something at the start, the network is going to forget, okay, what was said at the start. And it's basically, it has like recency bias. So the key question is, how do we let a model look at everything at once? Um, and the way that works is we're going to kind of dive into attention. And so this paper we have, attention is all you need, kind of laid the foundations for some of these core transformers, a lot of the GPT models that you use on a database basis. And so the idea is, okay, let's say we have a sentence, dog chased the ball because it was fast. The model must connect the words across the distance, right? So the word it must be able to correlate to every single word in that sentence without having that sequential recency bias that an RNN has, right? And so attention lets that model decide what exactly matters um, to the word it. So essentially, not all words are important. I mean, for the sentence, the dog chased the ball because it was fast. The word the is not really important to it as much as the word dog is. And so that's why we assign different weights to different words. Important words get higher weights, less important words get lower weights. It's very intuitive in that sense. And so a little bit behind the mathematics of how that works is we have three components, three vectors, and we have a query vector for each word, and this each word creates a query, and that's essentially saying what am I looking for this word, right? And the key, which is what you compare the query to for every single key, is what does each word offer, right? So you compare the query with all the keys, you get similarity scores, that simple matrix multiplication. You do an outer product, so you kind of have a matrix for the queries and the keys on the outside, and you have the individual boxes showing the similarity scores, and then you turn that into weights to get softmax, and then you kind of incorporate the values for each individual word, which is what exactly does it bring to the table, right? So we have an example right here. The cat sat because it was tired. The word it, which is a query, looks at cat, another key, and sees, okay, high relevance, right? But then also looks at the word sat, which is, okay, low relevance. So across our vector that we generate, or the embedding, we're going to realize that we need to pull in info from cat the most in comparison to something like the word sat. And so that's how that works, is that like simultaneously we're now able to generate relevance embeddings for each individual word respective to each other. So this matrix is an n squared matrix. So if we have a sequence of size length n, then our matrix is inherently going to be n squared in terms of computation. So that's one of the biggest drawbacks of attention-based networks, is that they scale pretty bad. And if you have something, right, that has n squared, eventually it gets computationally expensive. Um, but obviously, I mean, there's been quite a bit of developments with subquadratic attention, trying to compress this down into, okay, an n by n matrix. Can we do it something under where we have like kernel approximations, where we develop kind of like a projection into a lower dimensional space? A lot of different methods, but there hasn't been really anything substantial that disproves this to a large degree and said, okay, this is the new popular method or the new way to go about this. A transformer is basically just multiple attention layers stacked together. We have the transformer block, which has self-attention, right? Self-attention is how we kind of implement attention within itself, so like within the same sentence. So words communicate with each other, and then feed forward, which is a simple neural network with multiple layers of neurons in one layer, multiple neurons in one layer, and then we kind of interconnect it. Each neuron connects to every single other neuron in the next layer. So just a simple feed forward neural network. And then we have adding and normalization, which keeps training stable. So basically you have dropout, different types of activation functions, a lot of those things. So a transformer is basically just a culmination of these things, with attention being the star of the story in that situation. And then we have the data flow, right? So you have the input sentence, the attention does the work right there. And then you have a feed forward layer, you repeat it multiple times, and then you stack these blocks together, and boom, you get a transformer. And at the core, that's what it is. And attention is a core building block for that transformer. So we'll go into a little bit of a live demo. I'm going to try my best to not have this issue, but before that, does anyone have any questions? No? Okay, so if you guys want to, you can open up a blank notebook. I'm going to see if I can kind of mess with this display thing so I can kind of actually go into Colab.
Not looking. Pressing. You just like moved it and it kind of broke.
Tried replugging it if it could, because I couldn't get to the collab anyways. Isn't
It wasn't updating.
no.
Um, so it's broke. Always tech struggles.
There we go. Looks promising.
That was USB. Run USB now source. Want to go back to HDMI 1? Yeah. Yeah.
Can't
Okay.
click it. I have to wait.
Oh, you have to wait?
Yeah. No signal. Just
Just keep plugging back in. HDMI 2.
maybe it's a different input this time. I don't know.
I doubt. I don't know. Might be the case. Exactly. Is there another HDMI? Actually, you can also just move to that chair if you want.
Yeah, this works. Yeah.
Go to USB.
Right here.
Yeah. Try. I think. Try PCN maybe.
This one.
Yeah. Maybe what is it here?
Okay, I'm gonna end the broadcast. Let me see.